That's not true, right? Even when you go to 2, that's not true. Not all, if you write du dt equals f of u v and dv dt equals g of u v, you cannot necessarily write this as du of some f and dv of some f, right? What conditions do you need on f and g such that you could write them that way?
Should be harmonic equations.
Say again?
Should be harmonic equations.
I'm sorry, I still don't hear.
Should be harmonic equations
Harmonic equations,
or analytical.
analytical equations. That's not enough. Not enough. You mean f and g can't be any old functions of u and v? No, they could be analytic. They could be they could be. You could have them being perfectly power, so you can have them analytic. To me, I mean, maybe to real mathematicians it means something different, but it just means that it could be written this way. And that's not enough to guarantee, okay, I'm basically always assuming that they're of this form, and this is not enough to guarantee that that there exists some function f such that this is, what do you need?
I think they have to be constants.
df be constant? I'm sorry, what does that mean?
The function f and g
Yes?
do not depend on u and v in either way.
No, these are supposed to be coefficients.
So
These are Taylor series, two-dimensional Taylor series. Okay, so this I accept. I assume this, but that is not sufficient to guarantee this. The existence of an f and v such that this is the case. Okay, I will tell you. I personally have forgotten the exact thing, but I think I can get it back. But I know when I learned it. I learned it when I was about in the beginning, the second year of college. University. So I think you have this somewhere in your curriculum. When you're reminded, you will say, oh yes, of course. I say, first thing I forget it right now, so I'm waiting for you to give me the answer.
Something like the condition for stream function.
Something like that, yeah, it's a little kind of like that, yeah. Oh, come on, somebody can give another guess. Come on. So it's something primitive, something really that you learned a while back. Really, I should give you the answer? Nobody's going to rise to the challenge? Okay, I believe that it's that. Now you see, you'll never forget it because, of course, I did all this. Okay, certainly, if this were the case, if it were equal to that, then you would have to have, we know that partial derivatives commute, right? We would have d squared f du dv, and that would be equal to df dv, and would be equal to dg rather, du. Okay? So certainly if this were the case, if this were the case, then you would have dg du equals dv df dv. Okay? I claim, and for reasons that I can't remember right now, that this is not just, the implication does not just go this way, it also goes this way. That is to say, if you, I should say, this would imply this. I claim that that is what you need to make that the case, to make this, to make this representable this way. Okay, and I believe, isn't that, does this have to do with Cauchy-Riemann or one of those theorems, Gauss's theorem or Stokes' theorem or somebody's theorem, right? This cross derivative.
Is that Clonard's theorem?
Whose theorem?
Clonard? Clonard?
Spell it.
C-L-A-I-R. yes. CL.
I don't know this name. I mean, it could be that some theorem that which has been given a name that other people took as a consequence of other theorems. No, doesn't this sound familiar to
Yes.
people now? Okay, and didn't you learn it some time ago? Like in
Second year
maybe second year?
undergraduate.
Yeah, second year undergraduate. It was about, as soon as you learn multivariable calculus, you learn something like that. And then you call this thing a gradient field. Something is a gradient field if and only if. And I think isn't this saying that the curl is 0? Something's a gradient if and only if it's a curl? I mean, again, those are there are many things that are easy to prove one way but not the other. Certainly you know that this is 0 and you can easily prove it by the definitions. But supposing, okay, so that part's easy, but supposing you know that this is true. Do you know that this is true? Well, I believe, again, I'm not absolutely sure, but I think that's true. I think that's so, and I think that's what we just showed here. This, you can see it looks like a curl. dg, the second function, its derivative, so this is it's the second function with respect to the first variable minus the first function with respect to the second variable. So I think this is saying exactly this. And this part is very easy to show, but then this part is harder, and that's why it's given the name of theorem. And for all I know, one of the many names for that perhaps is that, or what names are you associating with this theorem? It's something like, isn't there Gauss or Stokes or somebody in there? Stokes, yeah, okay.
Something like that.
Okay, anyway, so that's what we're talking about, is gradient systems. They're not all like that, just some of them are like that. Okay, so that's what's written here, right? So let us consider the ones that, okay, and this gradient is not a gradient with respect to space. That's one of the reasons I was willing to spend all this time on this. You can see this is a gradient with respect to these variables u and v, without space in there right now. Okay? So for a gradient flow, if a flow is of this form, then when you take the Jacobian of this right-hand side, remember the Jacobian is a bunch of first-order partial derivatives, but these are already partial derivatives, first order. So what you get is called the Hessian matrix. It's the matrix of second derivatives. Okay? So it looks like that. And it is symmetric. This is kind of what we were doing over here. It's symmetric. Okay? It doesn't matter whether you take which order you take it in. We know that the derivative of if you take the derivative with respect to u1 and u2, that's the same as taking the derivative with respect to u2 and u1. And what do you know about symmetric matrices and their eigenvalues? They're all real, just so. They are all real, and so they have no complex eigenvalues, and so there can be no Hopf bifurcations. Okay. So a system, if you can write this system in this form, there are no Hopf bifurcations. The idea is that the dynamics here are that phi decreases monotonically. You're going down the gradient, just going downhill, right? And so you don't waste time oscillating, going around. You're on your way down. The phi decreases monotonically either to minus infinity or to a point where the gradient is 0, a minimum, a bowl, and there are no limit cycles. So you can prove, you might wonder, we saw that there are not merely Hopf bifurcations that create limit cycles. There are other ways to create limit cycles as well. And how could you prove that a system has no limit cycles? That seems, you have to know all of its solutions. Well, in fact, if the system is of that form, then it has no limit cycles. You know this. So if your algebra shows you that, you do not have to find all the possible trajectories and show that none of them are limit cycles. Now, let us, that's part's done. Now let's generalize. We've done all this with space. There's no space in here. Let's generalize to include space. These are u and v, just as u1, u2, u3. We don't have any space. Now let us put in some space. Let's turn these into reaction diffusion equations, where our reaction is of this special gradient form. And I remind you that this gradient that I'm talking about is not a spatial gradient, it's a gradient meaning with respect to U and V. Derivatives with respect to chemical species 1, derivative with respect to chemical species 2. And let us consider two possible on an interval. We're doing this in one dimension. Let us consider two possible boundary conditions, Dirichlet or Neumann. The Neumann would be homogeneous and the Dirichlet not necessarily. Okay, I'm just putting forth a problem. I haven't set any results. I'm defining a problem. Now I'm going to define this quantity here. Again, I'm not showing anything yet. I'm defining the Lyapunov functional. What is a functional as opposed to a function? This whole thing here is a scalar. I've taken this multidimensional object, and it's multidimensional because there might be several species, U, V, W, or U1, UV, U2, U3, etc., and because there's spatial dependence. So these are big objects, these things, these right-hand, these U's here are big objects with spatial dependence and possibly several species. And this thing here is a scalar, and that's what a functional is, I believe. A functional is something that takes a big object and turns it into a scalar, or maps it to a scalar. And so a classical one is energy, but this is a kind of an analog of energy. So we're going to call phi the potential energy. Makes sense, we're going down the gradient, we're going to lower potential energy. Okay, so it makes sense for the system to evolve towards lower potential energy. And we're going to define this, we'll just call this thing kinetic energy, why not? I mean, we can call it anything we want. So this is like a V, the du dx. Right? These are just words, this is just a definition. You'll agree that I have a right to define this thing, and I can put these words on it if I want, and hopefully they'll make sense. And now we seek, okay, so that's a quantity. And now we want to differentiate it. And this is the word I was looking for that the first day when I said, wasn't there a word in there? And I said, Frechet derivative. I said, okay, and that's what we're about to define, or a functional derivative here. So, okay, we know what a gradient is. We take f, so I'm now back to functions here. This f, that's why I don't have this funny, the calligraphic f. And I'm going to perturb it. And so I make a Taylor series, I do f of x, and then my next term is gradient f dx. That's just one of the ways of writing Taylor series, right? And this is a functional. That's why, unlike before when we had the Jacobian here, where Jacobian matrix times a vector, this thing here, this x and dx, are still vectors, but this f is a scalar. Okay? Hence my writing grad f dot dx, which contracts the thing to another scalar. Okay? So let me do the same thing for my functional, where I don't just have a vector x, but I have this fancy thing. I mean, it is a vector, but it's a complicated vector. We're viewing it as a bunch of functions of space. So I'm going to add a little bit of u, and again, to be fancy, I won't call it du, I'll call it a delta u with that little delta, and that means a change in a function. So a delta u, typically, here you have some, here you have x, here you have some function, u of x, and then supposing you do something to it, you put in a little, like that. That is a delta. You added a little thing like this. This is a delta u. Why do I keep having so much trouble? Delta u is also a function of x, and this thing here, this whole thing, is u plus delta u of x. Okay, so that's what we're imagining, is I'm taking my function and I'm changing it by a little teeny other function. I'm adding a little teeny other function. It doesn't have to be localized, but one usually imagines it to be. Okay. And now let me evaluate my functional there and do a Taylor series. So of course I do fu, and now I'm going to, excuse me, I'm going to take, I'm just writing the Taylor series. Okay, but I haven't done anything yet. it's defined, this df du had better be defined, excuse me, not, I want it to be defined such that just as could be seen as a way of defining the gradient, I want this to be true for every dx, that if I move x by dx and subtract f of x, I'm getting a vector dot dx. So too, I want to define something that has this property. Okay, but I have not done it yet, and I'm going to do it in the next slide. And I see that people are getting tired, so let me encourage them. One more slide to go, I think. Is that true? No, 2. Okay, so let me write my f of u plus delta u. So I just recall my definition. My definition was that it was phi on this argument plus 1/2 d by dx of that argument squared. That's the definition of f. I've just practiced it on u plus delta u. Yes? Okay. And now let me do some perfectly legal operations. This is the first time I'm going to calculate. This thing here is a function, not a functional, but a function, and I'm going to write its Taylor series here. So I'm going to write phi of u, and the gradient of this with respect to its argument, the u's, dot du. Okay. And then this thing here, this is just a derivative, and I can just expand it as I usually do. It's linear function, du dx plus d delta u dx, and so on squared. I can then put this square together. I have this 0th order term, the f phi of u term, and I have the 1/2 du dx squared term, okay? And then I have the next terms, and the next terms are grad phi, and remember this gradient is taken with respect to the u's, not with respect to the x's. Gradient of phi dot delta u, you can see because I've taken a dot product with respect to u, not with respect to these. So it has something to do with derivatives with respect to u and v, or u1, u2, it's these kind of derivatives here. As opposed to these, which are derivatives with respect to x. Okay, and my next term was the cross term, so the 1/2 with the 2 goes away, and I have du dx times delta u dx. And then I have higher order terms. So let me look at these linear terms, and I'm going to practice integration by parts to remember that my purpose, I want to get a delta u out of here, because this is now going to be my definition of my functional derivative, df du. I need a delta u and I need a delta x, a dx and a delta u. And I don't have that yet. I'm almost there, but not yet. I have a delta u here. So this thing I'm going to treat with integration by parts. So I can never do integration by parts without writing u, v, du, u dv, u times v, v du. Maybe you can do it. I won't do that. I'm just going to tell you what we're going to do is we're going to the uv part, we integrate this thing here, and that's easy since it's the reason we set it up this way is so that we can do that. We're going to integrate this part, and that just gives us delta u, fine, and that's the surface term. And now we have this with the second derivative of this, right? If this is u dv, then this is uv, and now we need v du. So we have the v here, and the du is the derivative of du dx. Okay, so everybody take my word for it that this is proper integration by parts? So recall the boundary conditions that we chose. The boundary conditions we chose were either inhomogeneous Dirichlet or homogeneous Neumann. And the reason for that was to control this perturbation delta u that was allowed. If u satisfies those boundary conditions, then delta u had better satisfy either homogeneous Dirichlet boundary conditions, because we want, if u is equal to u low and u high at those places, and the perturbation has to be such as also to satisfy that. And hence we know that du is equal to 0 at the boundaries. This is at the boundaries. Okay? So those inhomogeneous boundary conditions become homogeneous boundary conditions on the delta u. So that would go away for the delta u, right? If we had Dirichlet boundary conditions. But they would also go away for the Neumann boundary conditions, the homogeneous Neumann boundary conditions, because then that would be true of du dx. So either this thing disappears below here, the delta u has to be 0 on the boundaries, or the original u has to have its derivative be 0 on the boundaries. So in either case, this surface term goes away, and we're left with just this term. And we see now that we're finished, because what we wanted was for this thing to be an integral, the dx, and a delta u. And here it already is, and now this new part is an integral. The surface term is going away. You know whenever you're going to do theory and integration by parts, the surface term is going to go away. We have a delta u, and we have an integral. And so here we've written it that way. This is the 0th order term. This is the next order term. And so we define this to be the functional derivative df du. And we can now, okay, so we've defined it that way. And we can actually set, that's the integral, we can actually set this equal to this in the for the following reason. Because this is true for every delta u. And so we can set delta u to be a little delta function at any place. And delta u can have any nature. You can see that if this equality is satisfied for every point x, for every possible perturbation delta u, then it must be satisfied in general at every point. Okay, because this thing could be a delta function at every point in space, and hence we define df du to be what we were seeking was a generalization of the gradient, and we have one. We had the gradient, it was the gradient before, and now it also has a minus d squared dux squared term. That is to say, taking our original thing here, we have defined a generalization of a gradient system. We have du dt equals minus, before we defined a gradient system to be such that du dt is minus grad phi. Now we can define a more general gradient system to be such that minus du dt is df du, if you put in the diffusion like this. Okay, so we say that this is also a kind of gradient system where we are taking a functional derivative of this functional f. Okay, so that's it for now. We will continue in about 15 minutes.